Okay, thank you, Albert. So let's go on lecture 3 here, but there was some unfinished business from last time. We were talking about hypothesis tests, and I want to then extend this notion of a hypothesis test to explain how to construct what's called a confidence interval. And these are the all-important limits that you set on rates and parameters and so forth. And then what I would like to get into after that is a discussion of systematic uncertainties, which is probably one of the more difficult aspects of any statistical analysis. And then what I fear is that this topic of experimental sensitivity, that's going to probably get pushed into tomorrow, and I'll have to lose something from tomorrow, but I'll try to fit as much in as I can. So let me start with the discussion of what are called confidence intervals. And I want to explain how to construct such an interval by inverting a test. Now, first of all, what are they and why do we need them? What we talked about in the first lecture was what's called point estimation of parameters. That is to say, we constructed an estimator which gave us a number, a single number, which we used as an estimate of a parameter. Now, what we would like to do in addition to that is to report some kind of a interval whose size reflects the accuracy of that parameter estimate. So we want to give some kind of a range of parameters, and we want to say that the parameter's value we think is probably in some sense within that range and probably not outside that range. And so the frequentist construct that plays that role is what's called a confidence interval. I need to be very careful about what it says for that I think that the parameter is probably in the interval. That's a bit subtle. All right, now the way that we do this in the frequentist game is the following. It is very closely related to the type of statistical test that we discussed yesterday. And so let's suppose that I have a parameter theta. Let me get my pointer working here. Sorry, what's going on? Let me get, So let's suppose that I have a parameter theta. And what I want to do is that constitutes a hypothesis. That is to say, that parameter lives in the context of some probability model for some data. And so what I want to do is I want to set up a test of that hypothesized value of theta. Now let's focus first on an individual value of theta. Once I've figured out how to do that, I'm going to repeat the exercise for all values of theta. So what we need to do for a value of theta is to set up a critical region. That is to say, you find a region that has this property that the probability to find the data in the critical region under the assumption of theta, that should be less than or equal to the size of the test alpha for some pre-specified alpha, like 5%, say. And then you make the observation, and if the data are observed to fall in the critical region, you reject that hypothesized value of the parameter. Now, having done that for one value of theta, do it for all values of theta. Some values will be rejected, others will not be rejected. And the set of theta values that are not rejected in this test of size alpha are said to constitute a confidence interval. And we say that the confidence level, or CL, of the confidence interval is 1 minus the size of the test that you use. All right, so if alpha was 5%, you would say that this is a confidence interval at 95% confidence level. So that's the basic idea of a confidence interval. Now, equivalently, what we can do is, we saw last time that there was a relationship between the type of a test where you accept or reject a hypothesis and a p-value. We can say that the critical region of the test is simply the region of the data space where the p-value would be less than alpha. So what we can therefore say is that this confidence interval is simply the set of parameter values for which the p-value is less than alpha. That's an equivalent way of saying the same thing I said on the previous slide. All right, so every value of theta, you can compute the p-value. If it's less than alpha, you reject it. It's outside the confidence interval. If it's greater than alpha, you don't reject it. It's inside. All right. Now, what you'd like to find, of course, when you're establishing an interval, is the boundary of the interval. I mean, that's what determines the interval. And that's the value of the parameter where the p-value is just at the limit. That is to say, the p-value is just equal to alpha. And so that provides actually the recipe for determining the edge of the confidence interval. Namely, you set up a formula for the p-value, you set that equal to alpha, and you solve that equation for the parameter. That gives you the parameter value that's just on the boundary. Now, and we'll see an example of doing that in just a second. Before I go to a simple example, let me just mention, suppose you had a multidimensional parameter space, so not just an individual parameter theta, but some vector of parameters. Well, we can use the same basic idea, which is to say that you compute a p-value for every point in the parameter space, and you find the region in that parameter space where the p-value is not less than alpha, and that forms a confidence region. Okay, so the boundary of that region is determined by the same criterion. That is to say, that's the region where the p-value is exactly equal to alpha. I'll use the word interval if it's a single parameter. I'll use the word region if it's two or more dimensions. Same basic idea, though. All right, so now let me mention what is a very important property of confidence intervals, perhaps the quintessential property, and that is what is called the coverage or coverage probability. The idea is the following. Somewhere in this parameter space is nature's true value, we hope, right? And let's suppose that the true value is rejected. Well, then that means that it's not in the confidence interval. So what's the probability for that to happen? Well, the probability to reject the true value by construction is given by the size of the test. Right? If it's continuous data, it's equal to the size of the test. If it's discrete data, then it's less than or equal to the size of the test. That's something I didn't introduce this term, I think, yesterday, but this is also what's called the type 1 error rate of the test. All right? That means that the probability for the interval to include the true value of the parameter has to be 1 minus that. Right? So in other words, if there's a probability of alpha that the true value is not in the interval, there's a probability of 1 minus alpha that the true value is in the interval. And we say that in that case, the confidence interval covers or includes the true value of the parameter with this property at least equal to the confidence level. And that's often quoted as the quintessential property of a confidence interval. It covers the true value of the parameter with the probability of 1 minus alpha. That assumes that you've set up the game so that somewhere within your set of theta values, there is a true value somewhere. So it assumes the composite hypothesis indexed by this parameter theta. It assumes that for some value of theta, there is a true value. All right, so let's see, why is this not advancing? Let's do an example. So let's go back to the case that we considered yesterday of observing a Poisson distributed value n, and the mean of the Poisson variable is equal to s plus b, where, as before, s is the expected number of signal events and b is the expected number of background events. And let me assume, as before, that b is known, but I think in the example that we talked about yesterday, b was 0.5. Now let me suppose that b is 4.5. And we observe 5 events. Now, that's not horribly unusual, because if the mean of a Poisson variable is 4.5 and you see 5 events, then let's consider first for a second the hypothesis that s is equal to 0. Well, that's just going to be slightly less than 50%. In other words, the probability of seeing 5 events or more under the hypothesis that the mean is 4.5, that's just slightly less than 50%. So there would be no reason to reject such a hypothesis. That would not be small. On the other hand, we can consider large values of s and ask if they are compatible with this observation of, say, only 5 events. And we can try to see which values of s are compatible with the data and which values are not. So I want to consider now high values of s. And I need to ask, what is the relevant alternative to testing a high value of S? Well, a low value of S, or 0. Right? So this is going to lead to an upper limit on S. I want to see what values of S that I can test and hopefully reject on the basis that they predict too many events relative to what I saw, which is to say only 5. Right? And so what is the region of even more incompatible data? Where do I put the critical region in such a test? Well, if the alternative to a high S is a low S, I put the critical region where there is a high probability under the assumption of low S, which is to say low numbers of events. That means that I define the p-value of a hypothesized value of S to be the probability under the assumption of S to see as many events as I saw or less. So this inequality is the other way around. It's the opposite way around relative to what we talked about yesterday when we were testing S equals 0. When we tested S equals 0, the relevant alternative was some positive high value of S. Here, when I'm testing a non-zero, say high value of S, the alternative is a low value. All right, so this inequality flips around. All right, so my recipe for determining then the upper limit on S, that's going to be the value of S for which the p-value is just equal to the size of the test that I want to carry out. So let's suppose that I want this upper limit to be at 95% confidence level. Then I will use a value of alpha for the test of 5%. And the recipe is that I set alpha equal to this p-value. And when I solve that for S, I'll call that my upper limit S up. So here I've already labeled that S up. So, all right, what is this probability? That's simply the sum from n equals 0 up to the number that I observed, which is 5, of this Poisson probability with a mean of S plus B. And so I suppose that you could write a simple computer program to solve this. What I'll tell you quickly is that there's a trick to summing Poisson probabilities. These can be related to the cumulative distribution of a chi-squared distributed variable. That's a slightly obscure piece of mathematics, and don't get confused into thinking that there is a chi-squared distributed variable involved in this problem. No, the data are Poisson distributed. But nevertheless, there is simply a mathematical identity that relates the sum of Poisson probabilities to the cumulative chi-squared distribution. And if you exploit that trick, then you can solve this equation in closed form for the upper limit S up. And it's then 1/2 times the inverse of the chi-squared cumulative distribution for 1 minus alpha with a number of degrees of freedom given by this expression here. It's related always to the upper limit of the sum, and then minus the expected number of background events. So before you look at the answer, you've probably already seen the answer. Think a little bit intuitively. What do we mean by this upper limit? I want to find the value such that there's a 5% probability to see 5 events or less. So what would be the mean of a Poisson variable that has that property? Well, you probably think maybe 10 or 11 or something. And so indeed, that's the case. It turns out that that value minus the expected background of 4.5 gives you an upper limit on S of 6. So if you had a Poisson distributed variable with a mean of 10.5, then there would be a 5% probability to see 5 events or less. Right, that's the sense of the upper limit. All right, so here's a graph then of what these upper limits look like. So here's the upper limit at a confidence level of 95% as a function of the expected number of background events for different values of n, for different numbers of the number of events observed. All right, so we were, let's see, it was 5, right? And the B was 4.5. So hopefully that led to 6 for the, I forget the exact numbers, it doesn't matter. Anyway, you can look up the numbers. It was 5 events observed, that was it. And this led to an upper limit of 6, that was it. All right, now one of the things that you can see in this set of curves is that they decrease, right? That just emerges from this formula because I subtract b here. It's got a minus b. It means that the formula naively goes negative. In fact, that doesn't mean that the upper limit is literally negative. What that means is that if you test all positive values of s, that for all values of s, maybe you can get a p-value less than 5%. Right? That would be the case, for example, if you observed 0 events and you had b of whatever it looks like there, slightly less than 3. Right. So let me point out another thing about this set of curves. Let's see, if we consider the limiting case where b goes to 0, then suppose you observed 0 events. Then that value right there, so the upper limit at 95% confidence level, is very close to 3. It's 2.99 something. But that's a number that a lot of physicists keep in their head. That is to say, if you have an experiment where the expected number of background is very small, and you observe 0 events, what's your upper limit on the number of signal events? 3. Okay, let's go on. Here are a set of numbers which are I've made up, but it's close to experiments that have occurred in the past, and that's the following. Let's suppose that the expected number of background events is 2.5, but you observe 0 events. Well, that can happen, of course. I mean, n is a Poisson distributed variable. It fluctuates around. For any value of the mean, there's a certain probability to get 0, and suppose you did. Now, furthermore, let's suppose that you had chosen a confidence level of 90%. Now, 95% is most often used by the LHC collaborations, but in other fields, a different value for the size of the test is used. And in particular, in neutrino physics for many years, 90% was more often used, I think still is. And so let's suppose that we had taken 90% for the desired confidence level. And you plug these values that we saw here into the formula for the upper limit, and we get a negative value. All right, we get minus 0.2 roughly. Now that's a little bit crazy. What does that say? That's supposed to be an upper limit. But maybe if this S represents a cross-section for a signal process, you know it has to be greater than or equal to 0 even before you did the experiment. And so it would seem a little bit silly to publish a negative upper limit as the result of your expensive experiment. You knew that it was non-negative even before you spent a dime on the experiment. But so the physicist is obviously unhappy with this procedure and goes and complains to the statistician and says, what's with this crazy procedure? And the statistician would say, look, this is all fine. The confidence interval is designed to cover the true value of the parameter with a probability of 90%. That means that 10% of the time it has to miss. So clearly this time it missed. And this is quite interesting. It means with these confidence intervals, sometimes, not always, but in particular in this case, you can know afterwards whether or not the true value is inside the interval. And in this case, you know that it's not. And that is not such an uncommon dilemma, particularly when you're testing parameter values where you have very little experimental sensitivity. So for example, if you test very small values of S. So how do we proceed? What does this poor fellow do? Well, you might say, let me go back for just a second. If we look at this set of curves here, you can see that these values here, what do they represent? That's the value of S such that there is a 5% probability to see the number of events you observed or less. And so if you change the confidence level, say to 90%, that would just shift the entire family of curves down, right? Because then the limit would be the value of S such that there's a 10% probability to see as many as you saw or less. All right, so the whole family of curves just shifts up and down when you shift if you choose a different confidence level. And so the poor physicist says, all right, maybe I shouldn't have used 90%. Let me use 95%. And that shifts the curves up. And it shifts that negative limit, in fact, from minus 0.2 to roughly plus 0.5. And so the physicist is very happy. And so not only is it a positive value, but it's in fact, it's a good positive value in the sense that it appears to be naively a very stringent limit. It's excluded a lot of values of S because it's quite low. But all right, maybe the physicist gets a little too clever and says, all right, since I got so much benefit by tweaking my confidence level, perhaps I should choose 0.917923. And then you get an upper limit of 10 to the minus 4. And of course, you can tweak it however you'd like, and you can get an arbitrarily small upper limit. So this is clearly crazy, but why? Well, let's think a little bit about why this is not the appropriate procedure. First, we said that the size of the test is a pre-specified constant. You're not supposed to go adjusting it after the fact. So you choose the confidence level, and you need to stick with that, right? So let's suppose, however, that you had chosen 95% to begin with, that was a possibility. Still, let's do a reality check on this upper limit of 0.5. Remember that the expected number of background events, that was 2.5. And so how can I characterize somehow the intrinsic resolution of my experiment? Remember that the standard deviation of a Poisson distributed variable is equal to the square root of the mean. And so that means the standard deviation of n is at least root 2.5, which is 1.6. So how can I be quoting an upper limit of 0.5 if I expect this background level to be fluctuating around by an amount of typically 1.6 upon repetition of the experiment? So how can the limit be so low? Well, one of the ways of addressing this issue, or one of the things that we do to address this issue, is the following, is that you would report the observed limit, right, using whatever procedure, not necessarily this procedure, but whatever procedure you use, you would report the observed limit. But then in addition, it's always important to provide some kind of measure of what we call the experimental sensitivity. And in this context, what that would mean is the following. Let's suppose that S was equal to 0, and you were to generate Poisson distributed data under that hypothesis with B equals 2.5. Then upon every repetition of the experiment, you would get a certain upper limit. And here on the right, I've shown the distribution of upper limits that you would get in the absence of a signal. So for S equals 0. And you can see that contribution there just on the left. That's the one at 0.5. But of course, you wouldn't usually get that. You would usually get one of the values closer to the middle of the distribution. And in fact, the mean of this distribution is 4.44. And so that now has become the custom. You report two numbers. You report the observed limit, and in addition, you report something like the expected limit. Sometimes we give the mean, other times for sort of technical reasons, we give the median. It wouldn't matter very much in this particular case, but you give some measure of what you would expect the limit to be under the hypothesis of background only. Right. All right, that's all quite subtle, but that's typically the way it's done. You report both an observed limit and an expected limit. Now, let's see, I see I'm going on to another topic here. Before I leave this topic, perhaps I should mention just a few things. This problem of, for example, getting limits that are small relative to your experimental sensitivity is something that's troubled us for many years. And there's been a lot of work on developing procedures that don't suffer from this pathology. Let me just mention a couple. There's so-called Feldman-Cousins limits that suffer substantially less from this. There is the so-called CLS method. In the extra slides, but these are actually the extra slides from lecture 2, I have some further information on that. I felt that if I went into that in detail, it would just take up an additional hour, and so I'm not going to go there now. I'll let people pause and digest the basic idea of upper limits, but then just to warn that very often in particle physics, we use one of these other techniques, such as CLS or Feldman-Cousins or a Bayesian limit, in order to, at least in part, in order to get around this type of pathology that I've just illustrated. Now, let me go on. That was for a single parameter, which I called S. But now let's suppose that I have a vector of parameters. The procedure becomes a little bit less obvious because it's less obvious on how to determine the p-value. And you know, how do you scan over a high dimensional parameter space and find the p-value for each one. It's starting to sound all a little bit difficult. So let me explain a way to construct an approximate confidence interval directly from the likelihood function. So this is much easier. So this is going to result in a quite simple procedure for determining a confidence region. And it is the procedure which is very, very often used in practice, but it is approximate. All right. So what we want to do is we want to test hypothesized points in this parameter space. And so I want to come up with some number which reflects the level of compatibility between this hypothesized point, theta, and the data. And on the basis of that number, I'm then going to compute a p-value. So what I'm going to do is I will compute the likelihood ratio, but the ratio of the following likelihoods. In the numerator, it is the likelihood of the hypothesized point in parameter space. In the denominator, I'm going to put the maximum of the likelihood. So theta hat there refers to the MLE. That's the value of theta that maximizes the likelihood. So you can see that this lambda, this ratio lies between 0 and 1. And clearly values closer to 1 I can take to reflect better agreement between the hypothesized theta and the data, because if they're in good agreement, it means that theta hat is going to come out close to the hypothesized theta, right? And low values mean poor agreement. Now, for, I suppose I could call it conventional reasons, it's actually a little more than that, but I'm not going to work directly with theta. Instead, I will define t theta as -2 times the log of that ratio lambda. So that's equivalent. Just logarithm is just a monotonic function, but this flips around your intuition as to what corresponds to good and bad agreement. So now, for example, if lambda is close to 1, then t is going to be low, right? So if lambda's poor agreement means low lambda, that means t is high. So you can think of the statistic t theta as being something like a chi-squared variable, right? High values correspond to bad agreement between the hypothesized theta and the data. So if I take that as defining really what I mean by a data that's compatible with theta and data that's more compatible with theta, that means that the p-value of a hypothesized point in the parameter space is going to be the probability under the assumption of that point, theta, to find the statistic t theta as high as the value that I observed or higher, right? Because higher values correspond to less compatibility. All right, so there's my formula now for the p-value. It contains the distribution of this statistic. I need to know, if I were to repeat the experiment many times, under the assumption of theta, how would this statistic t theta be distributed? Because after all, the data are fluctuating, it'll follow some distribution. All right, that might sound a little bit difficult, but there is a miraculous theorem that saves us called Wilks' theorem. And let me first give the simple version of Wilks' theorem. What it says is the following. It says that in the large sample limit, plus regularity conditions similar to what we went through on the first lecture concerning maximum likelihood estimators. So in this large sample limit, what it says is that the distribution of this statistic t theta under the assumption of theta is just a chi-squared distribution for n degrees of freedom, where n is the number of components of this vector of parameters. Done. So it's, strictly speaking, it only holds in the limit where you have an infinitely large data sample, but in practice, it is an excellent approximation even for moderate or smallish data samples. So let's assume that it holds. That means then that the p-value, if I go back to the formula, it's the integral from the, it's the integral from the t that I observed to infinity. So that's 1 minus the cumulative distribution. All right, and so that's my formula. The p-value is simply 1 minus the cumulative distribution of a chi-squared variable. So that's my notation there for cumulative distribution for the chi-squared distributed variable. Right, now I want to find the boundary of my confidence region. And so recall that the recipe for that is to take this p-value, set it equal to alpha, and then I want to find the locus of points in parameter space for which that condition holds. So first of all, let me set this guy equal to alpha, all right? And then I want to solve it first for t theta. That's my first step. So, all right, put the alpha on the other side, apply, let me assume that I have access to the inverse function of f, which I do. And so that means that t theta is equal to f inverse of 1 minus alpha. So this is the inverse of the cumulative distribution. That is simply the chi-squared quantile. All right, that's my first equation. But then remember also how I defined t theta. T theta was simply defined as minus 2 times the log of this likelihood ratio. So those two guys are equal. So now set those equal and solve that equation now for log L of theta. All right, and so basically it says that the region in theta space where that condition holds are the values of theta that satisfy this equation here. Log L, the log likelihood function, is equal to the maximum of the log likelihood function minus a numerical constant, minus 1/2 times the chi-squared quantile of 1 minus alpha. So that's, once you specify the size of the test and you specify the number of parameters we're talking about, this is just a numerical constant. So as an example, let's suppose that we take the confidence level of the confidence interval to be equal to the probability content within plus or minus 1 sigma of a Gaussian. That's 68.3%. And let's suppose that we have one parameter. So for that particular case, the chi-squared quantile for 1 degree of freedom of that probability is identically equal to 1. And so for that case, if that constant there is just equal to 1, then the edges of the confidence interval in that case are simply given by log L equals log L max minus 1/2. And that should ring a bell, because that was exactly the recipe that we had arrived at for estimating the standard deviation of a maximum likelihood estimator. And what that tells you is that the interval that goes from the MLE plus or minus, minus to plus 1 standard deviation, that is a 68.3% confidence level confidence interval. All right, so that's an important point of contact between the techniques of our first lecture and what we're seeing now with a confidence interval. So let me go back and show an example related to that. So here again is the likelihood function, the log likelihood function as a function of the parameter tau from that exponential example that we discussed on Monday. And so here I've repeated the exercise for only 5 events. So now the sample size is not that large. So now you can see that the log likelihood function is less parabolic than it was before. I don't know if you recall, but previously the example I think had 50 events and the log likelihood function was pretty parabolic. Now I've done it with only 5 events, so it's visibly asymmetric. So what you can do is you can find the maximum of log L, come down by 1/2, and that determines the value on the left here and the value on the right. And in addition, of course, you determine the MLE, right? And you might report the result of this measurement by giving the MLE plus this amount and then minus this amount. And that would be, in this case, 0.85 plus 0.52 minus 0.30. So that interval then is interpreted as a 68.3% confidence level confidence interval. And that sort of by default is what we use in particle physics. If somebody gives you a result like that and doesn't give you any further explanation, that's what you should assume, that the edges of that interval are a 68.3% confidence level confidence interval, very often written as a sort of asymmetric error bar. All right, I think that's all I wanted to say. No, sorry, there's a few more things that I wanted to mention about the multi-parameter case. So we said that for 68.3% confidence level and 1 parameter, this quantile that I've called here Q alpha, that was equal to 1. But now for a different number of parameters, this quantile will take on a different value. And so what I've shown in this table here is that for different values of the quantile, this tells you what the confidence level is for different numbers of parameters. So again, for n equals 1 and for the quantile equal to 1, that corresponds to a confidence level of 68.3%. But if you had two parameters and you still used the recipe log L equals log L max minus 1/2, so if you still used a quantile of 1, then the corresponding confidence level wouldn't be 68.3%. It would only be 39%. So the probability that such a two-dimensional region would cover the true point and parameter space wouldn't be 68.3, it would be 39.3%. And it decreases as the number of parameters increases. Right, so if you went down a further, so log L equals log L max minus 1/2 times 2, then of course you would get a larger region and a larger confidence level. Sometimes you want to actually specify what the confidence level of the region should be. So in this table here on the left, I've shown confidence levels that we might be interested in having, like 68.3% or 90% or 95%. And this tells you then what the corresponding quantile has to be for different numbers of the parameters. All right, so if you want, say, 95% confidence level, confidence region with two parameters, then you have to say log L equals log L max minus 1/2 times 5.99. Or you pick the number that you want. Now, was that it on confidence regions? Yes. So, all right, let's go on. And I think I have time to discuss systematic uncertainties and nuisance parameters. So let's suppose that we have a measurement that results in some data X, and I have a model for the probability of X that contains some parameter mu that I'm maybe interested in finding. And so let's suppose that this model is quite simple. It may have, in part of it at least, some linear relation between the parameter mu and X. That's the best model I was able to cook up. Now you can imagine that in a complicated experiment with many different complicated effects, that nature's truth won't be so simple. There's going to be small, subtle effects that will mean that the true model is some complicated thing like this dashed line. And so that means that if I use my simple model to estimate this parameter, that it's not the same value that I'm going to get if I were somehow to use the true model. Let's suppose that what I'm really interested in, say, is the slope of this probability in the limit that X goes to 0. So you can see that by using the approximate model, the solid line, I would get a different answer than I would get if I had access to this true model. So that means that my estimate of mu is going to be wrong. It'll have what we call a systematic error, right? An error because of the fact that my model was incorrect. And that's difficult to deal with. So it doesn't have to do with the fact that there's fluctuations in the data. This is actually an error in the value of the parameter because my model is wrong. How do we deal with that? You fix the model, right? So how do you change this approximate model into something which is closer to the true model? Well, in general, it involves inserting additional adjustable parameters into the model. This is not really a theorem. You could replace it by another model that only has a single parameter. But in general, what we do is we include additional terms into the model that involve further adjustable parameters. And in this particular way that I've drawn it, you can imagine that we could say, all right, in addition to a linear term, include maybe a quadratic term and something with x cubed. And so now I have additional parameters in the model. And my hope is that by doing that, for some point in this enlarged parameter space, my new and improved model will be sufficiently close to the truth that I will have eliminated that systematic error. Right? The model's now correct, so to speak, because for some point in this parameter space, we say that the model is now adequate to describe the data. All right, so that's the basic procedure. We start with some parameter that we're interested in. Right? So I'll call mu the parameter of interest. And I enlarge the model's parameter space by including what I call nuisance parameters. All right, so I suppose it's true that what is a nuisance parameter in one analysis could be a parameter of interest for somebody else in a different analysis. But in general, in a given analysis, we can distinguish between the parameters we're interested in and the other ones that are necessary for the model to be correct, but we're not interested in their values per se. And there's a correspondence then between these nuisance parameters and the systematic uncertainties, which they have been designed to eliminate. And so that seems to have solved the problem, right? I started off by saying that systematic uncertainties, that was the hardest problem to deal with. And now I said, well, just load up your model with lots of nuisance parameters and you're done. There is a price to pay. And the price of the additional nuisance parameters is that they decrease the sensitivity of the analysis to the parameter of interest. In particular, they would, for example, increase the variance of your estimate of the parameter of interest. They will increase the size of a confidence interval for the parameter of interest. Right. So how do we carry out an analysis that contains nuisance parameters? One of the ways that we do this, well, the basic way that this is carried out in a frequentist analysis is by constructing what is called the profile likelihood. So let's suppose that we have a likelihood that contains parameters of interest mu and some nuisance parameters theta, right? And let's suppose that there's n of the parameters of interest and m nuisance parameters. Then what we define is what is called the profiled values of, or constrained values of, these nuisance parameters. And these are defined to be the values of the nuisance parameters that maximize the likelihood for a specified value of the parameters of interest. Right, so first, I use this double hat notation to denote these profiled or constrained values. In some references, sometimes only a single hat is used, but then with a subscript mu. Anyway, there are different notations. But the point is here that these are computed by fixing the value of mu and then adjusting theta to maximize the likelihood. And then if you take those profiled values of the parameters and you evaluate the likelihood function with them, then that resulting function as a function of the parameters of interest is the profile likelihood. All right. So the profile likelihood only depends on the parameters of interest. The nuisance parameters are replaced by their constrained or profiled values. And what we can do now is the following, is that this profiled likelihood, it can be used in the same way that we used the likelihood function previously. All right, so the intervals and regions for the parameters of interest are going to emerge following the same sorts of recipes that we found previously, just using the likelihood. All right, so we'll see in a second how that works. So let's suppose that we have, the goal is to test different points of the parameters of interest, right? But what we want to do is to assert is the following, is that if we test and reject a certain point in mu space, what we want to mean by that is that its p-value is less than alpha for all possible values of the nuisance parameters. So this sounds like actually a somewhat difficult criterion to arrange for, but there's a trick that allows us to do this. What we're going to do now is the following, is we will test a hypothesized point in mu space using, again, a likelihood ratio, which is similar to what we saw before. But so in the numerator, I have the hypothesized value of mu, and for the nuisance parameters, I replace those by their profiled values. So theta double hat here refers to theta double hat of mu, right, as I've defined here. And in the denominator, I put the maximum of the likelihood function. So the single hats refer to the maximum likelihood estimators. So this so-called profile likelihood ratio is the generalized version of the likelihood ratio that we talked about 10 minutes ago, but now the nuisance parameters you'll see are treated in this particular way. Nevertheless, I can interpret its value as reflecting the level of agreement between the data and my hypothesized point in mu space. And as before, I'll use -2 times the logarithm of that ratio so that high values of the statistic T mu reflect poor agreement, less compatibility between mu and the data. Now, here's the miracle, is that Wilks' theorem still works, right? Wilks' theorem still tells you that in the large sample limit, and provided that the regularity conditions hold, then this statistic follows a chi-square distribution for capital N degrees of freedom, where you will recall that capital N, that was the number of parameters of interest. It's the number of components of mu. So that leads us very quickly to our answer. It says that the p-value of a hypothesized point in mu space is simply 1 minus the cumulative distribution of a chi-squared variable for capital N degrees of freedom. And provided that this asymptotic approximation holds, this large sample limit holds, that is true regardless of theta. It holds for essentially for any point in nuisance parameter space. So if I reject mu, because its p-value is less than alpha, that should hold regardless of theta. And so this criterion can be satisfied. If I reject the point in mu, it means it's rejected for any possible values of the nuisance parameters. So, right, that's just what I said. And so that means that the recipe to get the confidence intervals or confidence regions for the parameters is essentially the same as before. It simply means that you use the profile likelihood instead of the full likelihood. All right. Now, the problem is, when do you know whether or not this asymptotic limit is an adequate approximation? And that's difficult. And so in practice, in particle physics, we do a lot of Monte Carlo studies to try to validate that approximation to the extent that it's feasible. If it's not justified, then you can always use Monte Carlo to get the distribution of the statistic. And sometimes we have to do that. But in many cases of practical interest, it's possible to simply use the same basic recipe to find confidence regions. And that's a very important simplification. All right, so I think I just have time to go through a quick example that illustrates how that works. And so this is an example that it's not the most general likelihood in the world, but it covers a lot of ground. I think a large fraction of, say, LHC analyses would fall into this general category. So here it is. Let's suppose that we're looking for some signal process, and we think that if it exists, it would manifest itself in events that live in some region of phase space. And so I measure where the event is in phase space by measuring some variable x, and I put that into a histogram. And so let's say that the numbers n1 through n sub capital N, that's the histogram where I expect to see the signal. So for example, if you're looking for a Higgs-like particle, then this would be the histogram of the invariant mass of the Higgs candidates. All right, and you'd expect to see a bump somewhere in this histogram. And all right, let me suppose that the number of events that I find in each bin of this histogram, n sub I, let's suppose that they are independent and Poisson distributed with expectation values given by the following type of expression: mu si plus bi. So bi is the expected number of background events in the ith bin. Si is the expected number of signal events in the ith bin according to some signal model, my nominal signal model. So in the case of the Higgs, that would have been, say, the standard model. And mu is a strength parameter. That's going to play the role of my parameter of interest. So mu equals 0 corresponds to the background only hypothesis. Mu equals 1 corresponds to the nominal signal hypothesis. You could imagine something that looks like a Higgs, but maybe has a rate which is a factor of 2 greater or smaller. And so other values of mu are interesting as well. All right, how do I find Si and Bi? So the expected number of signal events in the ith bin is just going to be the total expected number of signal events. So that's related to the signal cross-section and luminosity, multiplied by the probability that X winds up in the ith bin. And so to do that, your signal theory, whatever that model is, has to predict the distribution of this kinematic variable, and you integrate that over the ith bin. I want to allow for the possibility, though, that I've had to introduce some nuisance parameters, NP, nuisance parameters, into the signal model. Right? So this SI could depend on some nuisance parameters. And similarly for the expected number of background events. In the ith bin, that's given by the total expected number of background events times the probability for the event to be in the ith bin. And that as well might have some nuisance parameters. And furthermore, the total expected number of background events, that's very often not known precisely, and I perhaps have to treat that as well as a nuisance parameter. So I mentioned that if you insert nuisance parameters into a model, that degrades the analysis. It decreases the sensitivity of the analysis to the parameter of interest. And so how do we combat that? How do we keep the nuisance parameters from spoiling the analysis? Well, what you do is you try to introduce into the measurement some sort of additional measurements, control measurements, which constrain the nuisance parameters. And so this could be a completely separate measurement. It might be just some sort of sidebands. But let me suppose for this example that I measure some other quantity and I put the result in a different histogram. And I'll call that M. So M1 through M sub capital M, these are the number of entries that I find in bins of this control measurement. And I've set up this control measurement so that the expectation values of these M sub I are some given functions of the nuisance parameters. Here, theta just denotes any of the possible nuisance parameters. All right. And so let's see, I did say these MIs are also going to be independent and Poisson distributed. And so that means that my likelihood function, which depends then on the parameter of interest mu and some vector of nuisance parameters theta, is going to be given by the product of Poisson probabilities for the primary measurement. That's the histogram where I expect some signal to perhaps manifest itself, times then the product of Poisson probabilities for my control measurement, where these u sub k's are given functions of the nuisance parameters. All right, so that basic form of a likelihood function is very often seen in particle physics. And then we follow through the program basically as I've described it before, which is to say we test different values of mu by forming this profile likelihood ratio, right? In the numerator, I have the profile likelihood. In the denominator, I have the maximum of the likelihood, right? And as I've mentioned before, the important advantage of this profile likelihood is that its distribution simply becomes related to a chi-squared distribution, right? It decouples from the nuisance parameters in the large sample limit. Now, let's suppose that what we want to test is the hypothesis of mu equals 0. And if we can reject that, we'll say that we've discovered the signal process. Now, let me suppose in this example, though, that the only conceivable or interesting alternative to mu equals 0 is some positive value of mu. So that is to say that if the signal is present, I only expect that to add events. That's not always the case. You could imagine like a neutrino oscillation experiment where if oscillations were absent, you'd expect a certain number of experiments. And under the hypothesis that neutrino oscillations are present, you might actually suppress the expected number of events. So you could have a mu that is effectively negative. Let me suppose that that's not what I'm talking about here. I'm talking about a new process that would only add events. So the relevant alternative to mu equals 0 is mu greater than 0. So that means that I will take the test, the critical region of a test of mu equals 0 to correspond to more events. And that corresponds to a data characteristic of mu greater than or equal to 0. And so in order to define the p-value to reflect that, here's the definition I use. I will define a statistic Q0 to be -2 times the log of this likelihood ratio lambda of 0, right? Because I'm testing mu equals 0. But I'll assign that value only if I see an excess of events relative to the background only hypothesis. And that would be reflected by having the MLE mu hat greater than or equal to 0. On the other hand, suppose you expect, I don't know, 100 events and you see only 50. Well, is that discrepant? Yes, but it's not the kind of discrepancy that I would exploit to claim discovery of a positive signal process. And so therefore we just assign a value of 0 to the statistic, right? So that doesn't reflect any discrepancy between the data and that hypothesis. Right. So that's the definition that is very, very often used, or something similar to that at least. And so what you need is to take Wilks' theorem. What Wilks' theorem told us was just the distribution of this part. And because we've then modified slightly the statistic, we need to work out the distribution. And that was done, we worked this out a number of years ago around the start of the LHC program. And so this has turned out to be very useful. Let me skip to the second formula. And what it says is that the PDF of the statistic Q0, under the assumption of mu equals 0, has two terms. It has a delta function at 0 with a weight of 1/2, and it has a chi-square distribution for 1 degree of freedom with a weight of 1/2. And you can understand that because if I go back, obviously if mu is equal to 0, then roughly half the time mu hat's going to fluctuate positive and half the time it will fluctuate negative. If it fluctuates negative, I assign a value of 0. So that's the delta function. If it fluctuates positive, if it fluctuates positive, then Wilks' theorem tells me that it's a chi-square distribution for 1 degree of freedom. All right, so that's the formula that we need to use to work out the p-value. We've also worked out in this paper up here the distribution of Q0, assuming a non-zero value of mu. It's a more complicated expression, but that's what you need, for example, to assess the experimental sensitivity. All right, this just illustrates, as before, what I mean by the p-value of mu equals 0. It's just the probability under the assumption of mu equals 0 to see Q0 as high as the value observed or higher, right? And then once I get that p-value, I'll compute the equivalent Gaussian significance as we discussed yesterday. And okay, so if you go back to the formula that I said, I'm going to skip quickly through the mathematics, but what you get is that because the cumulative distribution for Q0 is related to that of a chi-squared for 1 degree of freedom, that itself is related to the Gaussian cumulative distribution of the square root of Q0. There's a few lines of mathematics that will show you that that works, right? So that basically means that the p-value of mu equals 0 is simply given by 1 minus the Gaussian cumulative distribution of the square root of Q0. And then you'll notice that if I apply the formula for the significance, that involved the inverse of the cumulative distribution for a Gaussian. And so lots of factors cancel away, and I'm left at the end of the day with a very simple formula, and that is that the significance with which you would reject mu equals 0 is just given by the square root of that statistic. Done. So very simple formula at the end of the day. So if you do the measurement, if you see Q0 equal to 25, then you have a 5 sigma effect. So how do we test this? I've gone 2 minutes over already, so let me just wrap this up quickly. Here I've done a simple test in order to illustrate how large does the data sample need to be in order for this asymptotic approximation to be valid. So this is one of the tests that we did in this paper. Let's suppose that the histogram of n values just has one bin. So it's just a single number n, which is Poisson distributed with a mean of mu s plus b. Now, so mu is my parameter of interest. Let me take b as a nuisance parameter. Let's suppose that I don't know the background expected number of background events, so I have to treat that as a nuisance parameter. Well, how do you constrain that? Well, you do some kind of a control measurement where you set up a control measurement where you think you have only background, and I measure a number n, which is Poisson distributed with a mean of tau times b. So b is the same b as here, and tau is some scale factor which relates the control measurement to the primary measurement. It could be related to the width of a sideband, or tau can be known typically through some sort of Monte Carlo study. So let me suppose that tau is equal to 1 and that we know that. So here what I've shown is I've picked certain values for b, and I've generated Poisson distributed data according to this rule, and I've then plotted the distribution of Q0. And so the solid curve there, that is the asymptotic formula that I showed. that part there is the chi-square distribution for 1 degree of freedom with a weight of 1/2. And what you can't see here is the delta function at 0, but it's there as well. And then what are shown as the histograms are the distributions of the statistic from Monte Carlo, right? So there's no asymptotic approximation involved there. But so these are exact in that regard. And these use different values for B, 2, 5, and 20. And you can see that already for, say, B equals 20, the agreement between this large sample limit and the histogram for B equals 20 is really very good, out past Q0 of 30-ish. So this asymptotic approximation would be perfectly valid even to establish a 5 sigma discovery. Let's suppose that B is only 5. So this is really not what you would regard as an infinite data sample, right? You're only expecting 5 background events. And yet the asymptotic approximation agrees with the histogram really very well out to 20-ish, right? So it would be certainly adequate for a 3 or 4 sigma issue. Suppose you only had 2 events expected from background. All right, then it departs earlier, but nevertheless, that departure doesn't occur until maybe the 2 or 3 sigma level. So that's somehow an important lesson, is that even though we say that Wilks' theorem only holds in the limit of an infinite data sample, it is an excellent approximation even for moderate or quite smallish data samples. All right, so this is the final, I think I'll just show this final slide and then wrap up. I had to show a real example. And so here is the p-value of the background only hypothesis from the Higgs analysis from Atlas. Apologies to my CMS colleagues. They, of course, had a very similar looking plot. And so what we did here is we carried out a test of the background only hypothesis, but we carried out different tests that would be sensitive to different Higgs masses. And so what you see is that if you carry out a test where the alternative supposes a Higgs mass, which is say 115, then you can't reject that. On the other hand, if you test the background only hypothesis with this test that is sensitive to 125 GeV Higgs, then suddenly you get a very low p-value, and we can reject that. All right, what I need to get onto next is this issue of experimental sensitivity, and that's what's illustrated here by this dashed line in the middle. That tells you what the expected or median p-value would be under the hypothesis of a standard model Higgs. So that's the kind of thing that you had to show to your funding agency in order to get the money to do the experiment in the first place. That's a more complicated discussion, and I propose to push that into tomorrow's lecture. There's a few other things that I'll finish up from today's lecture already tomorrow. And for now, let me skip to the end. I think what might fall off this business about students' t-regression, I might have to push into the extra slides, but let me stop now. Thank you very much.
All right, Glenn, thanks very much for another nice lecture we just had. And as is traditional, we have some moments for questions. I don't see anything in the chat right now, but I see, there are things coming up there, but I see Quinn Yu has a question, so go ahead.
Hi, thank you. Thanks for your brilliant lecture. So I have a question about when you introduce the profile likelihood function, right? You have an extra Poisson term for the nuisance parameters, the UK, MK, those terms, and that remind me of in some. So I'm from Atlas. So in some Atlas search papers, the way that they define these terms seems to be putting some Gaussian constraint terms, and that gave me the impression that no matter what sensitivity you have to your mu, in the Poisson term, the original term without profile that you put on the the term that you show in the middle, you will always get how to say, your log likelihood function will decrease to 1 sigma, given your predefined 1 sigma of your nuisance parameter. So sorry if I don't describe it well, but
that's
the
fine.
symptom is that the positive error will always be less than 1. Isn't it a bit odd that it might violate the Wilks theorem that you propose?
It's not going to lead to a violation of Wilks' theorem. And in fact, constraining the nuisance parameters will help. So I'm not sure I see this. Let me first take a step back and comment, because I think maybe not everybody appreciated the first part of the comment. Here I've supposed that the control measurements come in the form of Poisson distributed quantities. And so the additional terms in the likelihood, the additional terms in the likelihood is this product of Poisson terms. Now, it could also be, for example, that I would have say a quantity, let me call it again M, and let me suppose that it was Gaussian distributed about theta, and it might have had some standard deviation, call it sigma M or something. And so then instead of this product of Gaussian terms, what I would have down here would be something like a term 1 over root 2 pi, sigma M e to the minus M minus theta squared over 2 sigma squared. All right, so that's another very commonly seen form for these additional terms in the likelihood that represent the control measurements. Now, that being said, there's no problem with that. I don't see an issue with violating Wilks' theorem or anything of that sort by including constraint terms that are of a Gaussian form or a Poisson form or some other form. So other than to say I don't see a problem, I'm not sure exactly what further to say on your question.
Yes, I will try not to say too much, but I was just wondering whether the fact that I saw a lot of people having very constrained positive error was due to the fact that they didn't define either the sigma m properly, or because their m's are not completely independent of nj. If you have any some kind of plots like this,
it can happen, for example. Yeah. Well, all right. So this word prefit versus postfit entered. So what can happen, for example, is that when I've just done the control measurement, I have a certain standard deviation. Let's say this m represents directly an estimate of the parameter theta, right? So let me call that sigma theta. And so that's, I think, my standard deviation of my estimate of theta before I combined everything into a single analysis. And so I would call that the pre-fit standard deviation of this particular estimated nuisance parameter. Once I do the analysis, I would then maximize this likelihood with respect to all the parameters, and I would then get, again, an estimate for theta and a corresponding standard deviation. Now, the standard deviation that results from the maximizing the full likelihood, I will call that the post-fit error. And so what can happen, of course, is that the post-fit sigma theta hat can be less than the pre-fit. Let me still call this maybe sigma m. And that can simply happen. It can also happen, for example, that the post-fit value of theta hat might turn out to be quite different from the initially estimated value of m. And so now you have put your finger on a particular problem, which is to say that sometimes what can happen is that the post-fit value that I get theta hat, if that turns out to be significantly different from m, you would take that to be a sign of a problem. You would take that to be a sign that your initial model assumptions were perhaps not fully correct. So I don't know, maybe that is that perhaps more the direction that you're getting?
Oh, so I was just wondering.
Yeah, we should also leave some room for other questions.
Sorry. Tell you what, if I haven't answered the question, send me an email and we'll take it up offline.
Okay, thank you. Thank you.
I saw Mohammed had a question. Mohammed Ali, you still have that, or you withdraw your hand? Or maybe he has left. I don't know. Then there's a question in the chat from Dimitri. In fact, he's putting up 2 questions now. Can you see those,
I
Glenn?
can.
Yeah.
So let me see, on slide 27, perhaps the cumulative distribution of f of q could be more characteristic of the position. Yes, absolutely. So you're suggesting that rather than show the histogram of Q0, that I show its cumulative distribution. And sometimes we do look at that. And I didn't, just because somehow people are more used to looking at histograms of variables. And so really just from a pedagogical standpoint, I thought it was easier to look at the PDF itself or the histogram itself. But you're absolutely correct that what I'm really interested in is the upper tail area. And in order to be able to see that more directly, the other quantity that we often plot is 1 minus the cumulative distribution. So it's directly related to the p-value. I think that answers your first point. And let's see, also, if one uses a weighted likelihood, so I have to know what kind of a weighted likelihood you're thinking about here, for the asymptotic calculation, would that break the regularity conditions? So let's see. All right, let me first of all point out that when I generate the data with this Monte Carlo, I'm just generating unweighted events, ordinary events. But as you've pointed out, Monte Carlo models very often don't produce just events. They produce events that come with a weight. And if that weight is equal to 2, you're supposed to think that that's as if the event occurred twice. Now, if that's true, that means that a Monte Carlo estimate of a distribution can be more difficult to interpret, but only in the sense that the statistical uncertainty in the Monte Carlo calculation that arises from the limited number of events generated, that could be more difficult to assess. But from the standpoint of using weighted Monte Carlo to determine the form of a distribution, that there's no particular complication there other than its statistical error. Now, does that break the regularity conditions required by Wilks? No, I don't see that as an issue there, because the using weighted Monte Carlo, that doesn't have to do with whether or not the actual data, the actual statistical model satisfies the criteria for the Wilks theorem. It would only be a problem with the histogram, not with the straight line. It could complicate the comparison of the Monte Carlo calculation with the asymptotic approximation. Let me leave it at that.
Okay, thanks, Glenn. Anybody else still has a question in this lecture? Okay, if not, then we wrap up here. Thanks for the lecture and the questions, Glenn. Thanks for the attendance. And tomorrow, don't forget, same time, we have our final lecture. See you then. Bye.
Thank you. Bye-bye.